Today, I will talk about, as the title says, non-standard accessibility relations for many varied modal logics. Well, in the talk, I will center in these five logics, five many varied logics, and I will say why these logics. After I will present the standard way of presenting the modal semantics for them. After I will say present what is the topic of this talk. Yes. If you have any doubts, you can ask. Well, I don't know how as you prefer. Well. Many varied logics were used for many things in the literature, for applications to paradoxes, for vagueness, we have technical applications of these logics. And the logics I will present here are the logic of paradox, the clean logic, Lukashevsky logics, LFI1, and RM3. Why I am presenting these logics? Because each one has a very particular conditional. And I will use the conditionals of these logics to define the accessibility relations of the modal extension of these logics. Yeah. Well, I will focus my presentation on two ways of characterizing the accessibility relations of the Kripke models for the many varied extensions or many varied the modal extension of these logics, the two-valued accessibility relation and the three-valued one. Well, as I said, I will focus on these logics. All of them share the same set of truth values. LP and K3 are very known in the literature. They share the same truth tables. They differ only on the set of designated values. K3 have only true, LP has the true and both, the intermediate true value. And conditional is defined as not phi or psi. As we know, in LP, this conditional does not validate modal exponents. K3 has no tautology. They, even although they are weak, they are quite useful for applications of semantics, theories of truth, for example. Well, we have here Federico that worked heavily on the strong clean semantics for this kind of applications. Well, as I said, the K3 had only true as the designated value, and so we define the consequence relation as preservation of truth. LP is the preservation of the true and the true and false. As L3 has this conditional as primitive, as we can see here. We have, for example, phi by phi as a theorem because it's also received the value true. The consequence relation of this logic is defined as in K3 because the true is the only designated value. LFI1, I will not use, for example, this is one logic of formal inconsistency. As we work heavily in Brazil, the logic that can recover instances of classical inferences by tagging propositional variables with the consistency operator. This logic has also the intermediate value as the designated, and so the consequence relation is defined as in LP, the preservation of designated values. The last logic I will focus on here is the RM3. This is a quasi-relevant logic. The difference from LFI1 is that when the antecedent is true and the consequence is both, the implication is false. And here we have the E also as a designated value, and so we define it the consequential relation as in MP. The modal extension of these logics, of many valid logic is in general received attention in the last 5-10 years, at least. And we have, for example, two ways of characterizing for example, the modalities. We can have bivalent modalities. We have many valid modalities. I will work on the second one. And so I will also focus on the modal logics based on these 5 logics I presented. And as I said, I will focus on these 2 ways of characterizing the accessibility relations of the modal semantics for these logics. The standard one, we have the standard definition of frame, that is a structure that has a set of words, an accessibility relation, a model. All of this is defined as usual in Kripke semantics. Here, the difference from the classical case is that we are working on many valid logics as propositional, and the quantifier is an infinitary conjunction here, and the possibility is an infinite disjunction. We have the propositional logic, the classical propositional logic. We have, for example, the logic K, because we have no restriction on the accessibility relation. Since we are working on 3 valid logics, we define this kind of notion of being strictly true and tolerantly true. We say that phi is strictly true in a word W if phi receives T in W, is tolerantly if it receives one of these 2, T or both. And phi is strictly true in the model if it is true in every word, and tolerantly true if it is tolerantly true in all words of the model. The consequential relation is defined as usual in the local characterization of the consequential relation. Here we have the preservation of strictly true, and this corresponds to KL3 and KK3, and L2 here corresponds to KLP, KLFI1, and KRM3, because these 3 logics preserve true and the intermediated value. So preservation of tolerant truth. Okay? Since we have no restriction in the accessibility relation, the propositional logic, as I said, if the propositional logic were classical, the resulting logic would be K. And so that's why I call here KL3, KK3, KLP, and KLFI1, because I put no restriction on the accessibility relation of these logics. Well, I focus here mainly on these principles. I will not work, for example, in extensions of K, because this working on the class of all models is sufficient to show what I want. Okay, so we have K, the definition of the interdefinability of box and diamond. Here is the inferential. It's important to say that this is. I put this because, for example, the logic K3, as it has no validities because of the intermediate value, it's convenient to present the differential version of the interdefinability. Okay. Well, I put here this table because to show which principle these logics validate. We have that K3 does not validate any formulaic principle, but validates the inferential ones. Well, the necessitation, since, for example, K3 has no valid formula, the antecedent of the necessitation is vacuously satisfied, and so this rule holds. So we have this in the standard way of characterizing the Kripke models for these logics. Well, now, we can extend these logics by imposing these kind of restrictions, and so we have the modal action, the modal action resulting from the imposing these properties, these conditions on the frames. But all of the, as I said, the way of characterizing the accessibility relation is similar to the classical logic. The necessitation is defined as an infinitary conjunction, and the box and the diamond, as an infinitary disjunction. And if then, for example, if the conditional of the conditional of if W sees Y, then phi receives one of the values on on Y. The conditional and the standard semantics is classical. The question is, what happens if we change the way of understanding this if-then? The first work, I think that Fitting was the first in proposing this kind of characterization that consists in changing the accessibility relation by a function. And so we have here, we can attribute true or false and intermediate value on the accessibility function here. And these models he calls implicational models because this now has a different meaning than the classical conditional. Well, he does not work with the diamond, but a reasonable definition of the reasonable definition of the semantics for the diamond can be given as this conjunction here, in also an infinitary disjunction. In the two-value case, we have the standard accessibility relation. Now the difference begins when we work on three-valued accessibility function. This arrow in Fitting works has this meaning here. Is the implication of Heyting algebra. And the conjunction is the usual, takes the minimum. What changes here is the implication. So if we take this implication here and understand and characterize the modal semantics for the logics I presented before, with this condition, with this table, we have this. We have the failure of the axiom K in LP. Well, here it fails by the reason that K3 has no validities. It fails also in R3. The definition of the box fails here. Also, the inferential version fails in R3. And the necessitation rule remains untouched here. It holds in no logics by following Fitting's characterization. Well, what happens if we change the way of understanding this arrow by giving the same by changing the semantic condition of this, taking the truth condition of the condition of the logic? Okay. For example, if we have LP, this means this will correspond to the LP truth table of the conditional. What happens if we change this intuition? Well, I will call this modal logics KL with this asterisk. So as I said, the truth condition of box in LP and K3 is given by this table. Well, in K3 we have only true as designated, and LP we have both. And so, and the definition of this arrow is this. In L3, the definition of the arrow is this. The definition of the arrow in LFI1. Sorry, there is a typo here because this is should be I here. And finally, the definition of the arrow in RM3 is given by the condition, this condition. Okay. Well, by changing this way of seeing this characterization in this way I am proposing, we have this kind of situation. For example, now the necessity.
Can I ask you a question about the previous slide?
Okay.
So what about the assertion of the fact that Y is accessible from W? Just that gets always a classical value, or can it receive a non-classical?
Sorry, this can
fact that RWY, the antecedent of the conditional. Yeah, that.
Well, if you, for example, this takes E and this takes E, the implication will be C. For example, suppose that every can I use this?
Sure. You just turn it up.
Thank you. Suppose that we have a model that has these two words, and okay, all of the definition of the function, the accessibility function gives E for all of these arguments. Okay, so if if this receives I and this receives I, the implication here will give I. Actually, well, since we have only two words in this model, the conjunction here will give the disinfinitive conjunction will give I to the box. Okay. I just wanted to a question.
Yes. Well, another question. It's a good question, but I will leave it.
Okay. I really miss this kind of because in Brazil, in Argentina, they change it for the white. I hate them. Well, we have this situation. The necessitation rule is no longer valid in RM3. It's just it's easy to see. You take, for example, a valid formula. Since RM3, all formulas value there is no way of defining in RM3 a formula that receives only classical values. We have, for example, at least one non-classic values for in the case of RM3. If the formula is valid, there is at least one model that gives the intermediate value to phi. If the accessibility relation is true, the implication of model will be false to box. Okay, and so necessitation rule is no longer valid in this logic here. Well, the definition of the interpretability of box and diamond now is ruined, as you can see. Well, the only logic that remains untouched here is this, because this logic is quite close to classical logic. Indeed, it's maximal with respect to classical logic. I will not enter in the details of the extensions of the possible extensions of the logics I presented, but I would like to say some word about this. For example, since we now have accessibility function, we have more expressivity in defining the possible ways of extending the accessibility function of imposing conditions, for example. So in reality, we have at least two ways. Reflexivity, these two ways. And the difference is not innocuous. If you put this, we have some, you may have some extreme things. They also with respect to this. For example, if we take the logic LP and restrict with the reflexivity 1 here, we have counterexamples of both ways of the axiom T. Because the accessibility, now the accessibility relation, well, the semantic characterization of the box, the implication is the implication of LP. If the DR receives I and 5 receives false, box receives I. And so we have counterexamples for these two principles, okay? Well, if we impose this restriction, the reflexivity 2, this we no longer we validate these two principles. So the expressivity, the more expressivity we have to be careful about restricting the accessibility function. Well, what my initial interest of working on this kind of semantics was this correspondence theory, the correspondence theory, because as we know, there are correspondences between certain modal formulas and certain properties definable in first-order logic. And we know that the systematic study of such a correspondence is called correspondence theory. Well, the classic works is from Van Benten. For example, we consider a translation from the modal language to the first-order one. Consider this translation. And we can prove that given a model, we can define a first-order model so that this identity holds. This result is framed in classical logic. We know that we can generalize this correspondence for some logics. For example, I don't know how to pronounce his name, but I think that's Bruno Terrox. He generalized these results for the infinitary Lukashevsky logics, and Badia, Caicedo, and another person that I don't remember the name, generalized these results for some other many-valued logics. But both of these results presupposes the bivalence of the accessibility relation. Now, the question is, what happens? In this case, in the case of the infinitary Lukashevsky logics, they restrict the first-order models to the crisp models. Roughly speaking, a crisp model is a model that has at least one predicate that behaves as classical logic. In the case of their work, this is the classical predicate. The question is, if this behaves non-classically, what happens with this kind of translation. So a further step would be the extension of the definability results of these for these models that the accessibility function is mainly valued. In the case of the proof theory, well, for the standard way of characterizing the modal models for many valid logics, we have, for example, Priest's tableaus. We can present, for example, for some logics as Lukashevich logics. In the case of fitting, it was a logic based on the Heighten algebra. We can present or a sequent calculus or axiomatic calculus for them. But in this case, fitting shows that we need to enrich the language with proof constants. Each proof value must have a constant denoting this in the object language. Okay. In the case of in our case, the first thing that came to my mind was the tableaus. Is an extension of the past results that he provides tableaus for many valid logics, and so we extend these tableaus. And also, we have many rules for the accessibility. A rule for the R when, for example, we have, just to mention, for example, the R1, R2, or R3. And we have distinct ways of extending these rules in the branch. This is what I thought at first. It was the first thing that came to my mind, but I know that in proof theory, people do not like labeled proof systems, and so an interesting proof system would be a thing that it's not this, but I have to investigate more. Thank you very much.